Hey, welcome back to Math with Patrick. It's June 13th, and we need to solve problem number 164 from the Daily Epsilon calendar today. And we are going to try to find the number of Archimedean solids. And honestly, before seeing this question in the calendar, I had no clue what an Archimedean solid is or was. And so I think the first thing that we should talk about today actually are Platonic solids. And then after dealing with what a Platonic solid is, we can then kind of move the discussion over to Archimedean solids. So a Platonic solid is a 3D shape. It's a solid where all the faces are congruent, so they're all the same. And the shape itself, the solid itself is convex. And so that means it kind of is spherical in a way. And there are exactly 5 Platonic solids. And I have examples right here. They come in the shapes of playing dice usually. And so this is I would say like the smallest Platonic solid. I call it a D4 because it's a 4-sided die. You can also call it a triangular pyramid because there's like a triangle base on which the pyramid stands. And it's also called a tetrahedron, tetra being like the number 4 because there's either 4 vertices or 4 faces. And that kind of describes what this shape is. So this is our first Platonic solid. All of the faces are going to be equilateral triangles. And one key feature that I want to show you is that if you kind of look at it from, I guess, like the top, you'll notice that you can see 3 triangles join at one of the vertices. And so that idea of like faces joining at a vertex is going to be important when we talk about the other Platonic solids. And actually, let's do them a little bit out of order. So here you can see that there are 3 equilateral triangles all joining at a vertex. And so maybe you can ask yourself, what if we join 4 equilateral triangles at a vertex? And that question precisely gives you the D8, the 8-sided die. This one, I forget the name of, honestly, but sorry. One way to think about it is that it's kind of just 2 square pyramids glued together. Because you can kind of see the pyramid top, and there's another pyramid on like the other side. It has 8 faces. All the faces are equilateral triangles, and that is 4 triangles kind of joining up at a vertex there at the top. The next Platonic solid that you can make by using just triangles is the D20. This is an icosahedron. Icosa, the prefix meaning 20. And so here you could see that here's the 20 on the 20-sided die, and there are exactly 20 triangles on the D20. And if you look at the top, there are, any vertex could be the top really, but there are 5 triangles that are joined up at a vertex there. And so when we go back to kind of like whiteboard stuff, we can talk about why there isn't the next Platonic solid made out of triangles, because this is the biggest they get. The next shape we could consider for Platonic solids is the square, right? Moving from 3 sides to 4. This is our familiar D6. It's a 6-sided die. It's a cube. All the faces are squares. And that's kind of basically it. And then with the same idea that 6 triangles couldn't make a Platonic solid, here you can see at every vertex there are 3 faces, but 4 squares couldn't make another Platonic solid. I'll show that in a sec. Finally, we went from triangles to squares and now pentagons. This is going to be the last Platonic solid to talk about. This is a dodecahedron. The prefix dodeca means 210, so there's 12 sides on a dodecahedron. And they're all made up of pentagons. And so here you can see that at each vertex we have 3 pentagons that are joining up, and 4 pentagons would be too much. And here, let me demonstrate what I mean by too much. So with triangles, we saw that we could create a tetrahedron. We could create whatever the name for a D8 is. And then we could also create the icosahedron, the D20. And so that comes from the fact that we're trying to only use regular polygons, so polygons whose lengths are all the same. And so if we use triangles to start out, this is kind of going to be the beginning net of creating the tetrahedron. And so if I try joining 4 of these triangles all at the same vertex, this is going to be the beginning of the net of the D8. if we try joining 5 different equilateral triangles to the same vertex, this is going to be the starting net of the icosahedron, or the D20. The next thing that you could try is the 6 triangles all together. But as you can see, this is a totally functional two-dimensional shape. If you tile 6 equilateral triangles all around the same vertex, you're going to get a flat plane. So there's no way for us to create a rounded convex shape out of 6 triangles, and so we have to stop at the 5. The same thing kind of happens when we were working with the squares. This could be the starting net for a square, or a cube rather, but then when we try to add on the 4th, then we get something that tiles the plane. And so the next shape to try is the regular pentagon. Honestly, this one's going to be a little bit hard to draw, but once we tile these pentagons together, let's see, how is it supposed to look? Kind of like that. Let me fix this side just a touch. We're going to notice that there is a little bit of like kind of a missing gap right there. And that is just enough to kind of warp this flat shape into something a bit more spherical. And clearly another pentagon won't fit in there. And then if we try tiling hexagons, we're going to get something that perfectly fits in a flat plane again. And so we can't create a platonic solid out of hexagons. So these 5 nets correspond to each of the 5 platonic solids. Oops, I skipped over the D6. I was trying to go in order. The D4, D6, the D8, the D12, and then finally the D20. And then if you're into games that roll dice, maybe you're asking me, where's the D10? And I have one right here. This one is just not considered a platonic solid because each of the faces are not regular polygons. This is considered a pentagonal trapezohedron, which basically just means, so pentagonal means that there's 5 stuff going on here, and then not exactly sure why it's called a trapezohedron. I can kind of hear the word trapezoid in there. Anyways, this isn't a platonic solid though, because the faces, although symmetrical all around, the face itself is not a regular polygon. It's a kite, and the lengths of some sides are different from the others. So yes, it's a game die that you might play with, but no, it's not a platonic solid. So all that chatter though, I was only talking about platonic solids. I haven't been talking about Archimedean solids at all. And maybe the way to think about what an Archimedean solid is that we aren't restricted to only having the same shape. We could have triangles and squares. We could have pentagons and triangles. We could have squares, pentagons, and triangles. And kind of this loosening of the restriction of needing all the faces to be congruent to each other is going to let us explore what makes an Archimedean solid. Also, I looked up the name. It's just an octahedron. I should have figured that out. Anyways, here's our list of platonic solids. And one more thing I want to mention is something called truncation, which is going to help us generate some Archimedean solids. To truncate something just kind of means to cut it off or make it shorter. And one example of truncation actually is taking our D10. And if you imagine kind of cutting off the top and cutting off the bottom so that like this top vertex is actually a flat face, we're going to get a pentagon up here, right? Because like all 5 of these sides, instead of the vertex, each of the sides is going to create an edge. And so we'll have a pentagon on the top. And then if you take a look at the kite and imagine truncating the bottom, this face with like the 0 on it, I'm going to cover it up now, that also is a pentagon. So kind of interestingly, if you take some shape of a D10 and truncate the top and bottom, you actually just return right back to your dodecahedron. So this idea of truncation is actually going to help us generate our first Archimedean solid today. Let's take the tetrahedron and truncate all the corners. So cut off all the corners. You'll notice that here, if the corner is gone and we cut it off, we're going to just get triangles. And so each of the vertices here is going to turn into a regular triangle or an equilateral triangle. And if you look at this face and you think about cutting off each of the corners, we're going to get a 6-sided shape or a hexagon. So each of the existing faces of a tetrahedron can turn into a regular hexagon. And if you cut off just the right amount, they will be regular hexagons. and we're going to get equilateral triangles on all the corners. And so this first Archimedean solid is called a truncated tetrahedron because we truncate the tetrahedron. And so let me write that note down. And just like our tetrahedron, we can truncate our octahedron and we can truncate our icosahedron. So these again are like our triangle formed platonic solids, and you can truncate all of the vertices of this guy and you're going to get something called a truncated octahedron. And you can also truncate all the vertices on this guy and you're going to get something called a truncated icosahedron. This actually, when you truncate it, turns into a soccer ball. Maybe you've noticed on a soccer ball, it's made out of like, I think it's black pentagons and white or hexagons. And so when you truncate this kind of the right way, you're going to get a tiling, kind of a spherical object made out of pentagons and hexagons. And that exactly is a soccer ball or a football if you're, not from the United States. Likewise, we can also truncate our other two platonic solids. If you truncate the cube, you can kind of imagine cutting off all of these little corners. And so the square face is going to turn into an octagonal face. And then we could cut it off the right way so that all of the 6 square faces turn into octagonal faces. And all of our current vertices, the corners, will turn into equilateral triangles. So same thing with our dodecahedron. All of the vertices will turn into regular triangles or equilateral triangles. And then since we're cutting off each of the corners of each of the pentagons, essentially they're going to double in size. So our pentagons are going to turn into decagons. And so these are even more truncated solids made from the platonic solids that we talked about earlier. Another geometric process to talk about is called cantillation. It's kind of like truncation, but you're cutting off more stuff at once. And this image sequence that I found on Wikipedia kind of explains it pretty well, where if you start with a cube and you try to cantillate the cube, notice how these edges of the cube start being shaved off and the edges turn into rectangles. And if you keep shaving off the side or the edges of the cube, they'll turn into squares for like a split second. And then they'll turn into rectangles again. And if you keep this process going, you're actually going to get to the octahedron. This is considered the dual solid of the cube. And one way to think about going from like solids to their dual solids is either through the process of cantillation like this, or the idea where the face of a previous solid is going to turn into the vertex of another. So like see how we have 6 faces on the cube. We're going to have 6 vertices on the octahedron. Anyways, the important part though, for today's problem on the calendar, is that if we cantillate something uniformly, we're going to create more Archimedean solids. So if we cantillate a cube and we change all of the edges into squares, and we also change all of the vertices into equilateral triangles, we're going to get something called a rhombocubooctahedron. I've never said that out loud. So cantillating a cube gives us yet another Archimedean solid. Cantillating a tetrahedron also gives us another Archimedean solid. I believe lastly on the idea of cantillation and kind of dual shapes, is the idea that the icosahedron and the dodecahedron are both duals of each other. And in the middle, you can see that we have yet another Archimedean solid. You can even think about expanding these shapes rather than shaving off edges and sides as another way to kind of visualize or think about cantillation. Interestingly, tetrahedrons are dual to themselves. And so this process here of expanding and contracting just creates more tetrahedrons. But here you can see how the cube and then now the octahedron, these have these expanding and contracting ideas. They are dual to each other. And then so here we have yet another Archimedean solid as kind of this in-between of the icosahedron and the dodecahedron. Yet another 3D geometric process to talk about is rectification. This can help us find another Archimedean solid. To rectify something is kind of like to truncate it, but even more. So earlier we talked about truncation, where we just lopped off some vertices. And so you can see how this vertex turns into a triangle. And then here we have, regular octagons, regular triangles. This is one of our Archimedean solids. It's just the truncated cube. But if we keep expanding these triangles, then we're going to get something that we could call the rectified cube, although we already had a name for this earlier. We called this the cantillated tetrahedron. So interestingly, if you cantillate a tetrahedron or you rectify a cube, you get the same shape. It's this guy, the cuboctahedron. But what's kind of cool is that if you rectify a dodecahedron or an icosahedron, you get a new shape. We haven't talked about this one before. And so this process of cutting off these vertices and cutting it off so that this edge turns into a vertex. So see how like this vertex is now a triangle, this edge is now a vertex. So doing this rectification method, we can create an icosahedron, and this is another Archimedean solid we haven't come across yet. Unfortunately, we only have 4 more Archimedean solids to get through. Currently, we have 9 on the page. Here is the whole list that I've been working with, and there's essentially 2 more that we can find by truncating, and there's 2 more that have this kind of snub adjective at the start, and I'll show you what that means. So we can take our cuboctahedron that we have found. I think we found it 2 different ways. And if you truncate it, cut off all the corners, you're going to get the truncated cuboctahedron. And so this is 1 more Archimedean solid we haven't found yet. We can also truncate the icosahedron. That's the one we just found by rectifying either our D20 or our D12. So truncating that rectified shape. Yeah, you rectify it, then you truncate it, and then you can get yet another shape. Then the last 2 that we're looking at, here is the snub cube. I feel like this animation really helps. So you can imagine either taking the D6 or the D8 and expanding it out. This was our rectifying process, I believe. No, that was the cantillation process, where you could either shave off sides or you could just expand it out. And so you could imagine that those blue sides you could shrink back in to get a cube, or the red sides you could shrink back in to get an octahedron. Either way, once we've expanded it out, you can see that rotating the square faces or rotating the triangle faces creates more triangles where there was once squares. And so this rotating process creates our snub cube. And then finally, we can do the same rotating process to get the snub dodecahedron. So let's check out the little twisting animation. And so we can see that we start at one of our Archimedean solids we've already found, and then you can twist either the blue faces or the red faces, and the squares turn into more triangles. So here is our 13th and our final Archimedean solid for the day. Maybe you still might have some questions, because I honestly do too. I'm thinking, like, what happens if you keep applying those different transformations, like the rectification, the cantillation, or the truncations? Like, do we keep just returning back to the same solids, or will we create different ones that are non-Archimedean and non-Platonic? Truly, I don't know, and I'd have to explore this more. And honestly, the video's been going on for quite some time. So there's a lot more to explore, perhaps a lot more to discuss, but here is our 13th and final Archimedean solid, and I'm feeling done with this video at least. So thanks for coming along and discovering all of these Archimedean solids with me today, and I'll see you tomorrow. Alrighty, bye.